3. Sufficient reason. There must be a sufficient reason for anything to exist, for any event to occur, for any truth to obtain. 4. Pre-established harmony. T. The appropriate nature of each substance brings it about that what happens to one corresponds to what happens to all the others, without, however, their acting upon one another directly. Discourse on Metaphysics. 14. A dropped glass shatters because it knows it has hit the ground, and not because the impact with the ground compels the glass to split. 5. Law of continuity. Natura non facit saltus, literally, nature does not make jumps. 6. Optimism. God assuredly always chooses the best. 7. Plenitude. Leibniz believed that the best of all possible worlds would actualize every genuine possibility, and argued in theodicy that this best of all possible worlds will contain all possibilities, with our finite experience of eternity giving no reason to dispute nature's perfection. Leibniz would on occasion give a rational defense of a specific principle, but more often took them for granted. Monads, edit. Leibniz's best-known contribution to metaphysics is his theory of monads, as exposited in Monadology. He proposes his theory that the universe is made of an infinite number of simple substances known as monads. Monads can also be compared to the corpuscles of the mechanical philosophy of René Descartes and others. These simple substances or monads are the ultimate units of existence in nature. Monads have no parts but still exist by the qualities that they have. These qualities are continuously changing over time, and each monad is unique. They are also not affected by time and are subject to only creation and annihilation. Monads are centers of force, substance is force, while space, matter, and motion are merely phenomenal. He argued, against Newton, that space, time, and motion are completely relative. As for my own opinion, I have said more than once, that I hold space to be something merely relative, as time is, that I hold it to be an order of coexistences, as time is an order of successions. Einstein, who called himself a Leibnizian, wrote in the introduction to Max Jammer's book Concepts of Space that Leibnizianism was superior to Newtonianism, and his ideas would have dominated over Newton's had it not been for the poor technological tools of the time. Joseph Agassiz argues that Leibniz paved the way for Einstein's theory of relativity. Leibniz's proof of God can be summarized in the theodicy. Reason is governed by the principle of contradiction and the principle of sufficient reason. Using the principle of reasoning, Leibniz concluded that the first reason of all things is God. All that we see and experience is subject to change, and the fact that this world is contingent can be explained by the possibility of the world being arranged differently in space and time. The contingent world must have some necessary reason for its existence. Leibniz uses a geometry book as an example to explain his reasoning. If this book was copied from an infinite chain of copies, there must be some reason for the content of the book. Leibniz concluded that there must be the monus monadum or God. The ontological essence of a monad is its irreducible simplicity. Unlike atoms, monads possess no material or spatial character. They also differ from atoms by their complete mutual independence, so that interactions among monads are only apparent. Instead, by virtue of the principle of pre-established harmony, each monad follows a pre-programmed set of instructions peculiar to itself, so that a monad knows what to do at each moment. By virtue of these intrinsic instructions, each monad is like a little mirror of the universe. Monads need not be small. For example, each human being constitutes a monad, in which case free will is problematic. Monads are purported to have gotten rid of the problematic. One interaction between mind and matter arising in the system of Descartes. 2. Lack of individuation inherent to the system of Spinoza, which represents individual creatures as merely accidental. Theodicy and optimism, edit. Further information, best of all possible worlds and philosophical optimism. The theodicy tries to justify the apparent imperfections of the world by claiming that it is optimal among all possible worlds. It must be the best possible and most balanced world, because it was created by an all-powerful and all-knowing God, who would not choose to create an imperfect world if a better world could be known to him or possible to exist. In effect, apparent flaws that can be identified in this world must exist in every possible world, because otherwise God would have chosen to create the world that excluded those flaws. Leibniz asserted that the truths of theology, religion, and philosophy cannot contradict each other, since reason and faith are both gifts of God, so that their conflict would imply God contending against himself. The theodicy is Leibniz's attempt to reconcile his personal philosophical system with his interpretation of the tenets of Christianity. This project was motivated in part by Leibniz's belief, shared by many philosophers and theologians during the Enlightenment, in the rational and enlightened nature of the Christian religion. It was also shaped by Leibniz's belief in the perfectibility of human nature, if humanity relied on correct philosophy and religion as a guide, and by his belief that metaphysical necessity must have a rational or logical foundation, even if this metaphysical causality seemed inexplicable in terms of physical necessity, the natural laws identified by science. In the view of Leibniz, because reason and faith must be entirely reconciled, any tenet of faith which could not be defended by reason must be rejected. Leibniz then approached one of the central criticisms of Christian theism: if God is all good, all wise, and all powerful, then how did evil come into the world? The answer, according to Leibniz, is that, while God is indeed unlimited in wisdom and power, his human creations, as creations, are limited both in their wisdom and in their power to act. This predisposes humans to false beliefs, wrong decisions, and ineffective actions in the exercise of their free will. God does not arbitrarily inflict pain and suffering on humans, rather he permits both moral evil, sin, and physical evil, pain and suffering, as the necessary consequences of metaphysical evil, imperfection, as a means by which humans can identify and correct their erroneous decisions, and as a contrast to true good. Further, although human actions flow from prior causes that ultimately arise in God and therefore are known to God as metaphysical certainties, an individual's free will is exercised within natural laws, where choices are merely contingently necessary and to be decided in the event by a wonderful spontaneity that provides individuals with an escape from rigorous predestination. Discourse on Metaphysics, edit. For Leibniz, God is an absolutely perfect being. He describes this perfection later in section 6 as the simplest form of something with the most substantial outcome. 6. Along these lines, he declares that every type of perfection pertains to him, God, in the highest degree, Even though his types of perfections are not specifically drawn out, Leibniz highlights the one thing that, to him, does certify imperfections and proves that God is perfect, that one acts imperfectly if he acts with less perfection than he is capable of, and since God is a perfect being, he cannot act imperfectly. 3. Because God cannot act imperfectly, the decisions he makes pertaining to the world must be perfect. Leibniz also comforts readers, stating that because he has done everything to the most perfect degree, those who love him cannot be injured. However, to love God is a subject of difficulty, as Leibniz believes that we are not disposed to wish for that which God desires because we have the ability to alter our disposition. 4. In accordance with this, many act as rebels. But Leibniz says that the only way we can truly love God is by being content with all that comes to us according to his will. 4. Because God is an absolutely perfect being, Leibniz argues that God would be acting imperfectly if he acted with any less perfection than what he is able of. 3. His syllogism then ends with the statement that God has made the world perfectly in all ways. This also affects how we should view God and his will. Leibniz states that, in lieu of God's will, we have to understand that God is the best of all masters and he will know when his good succeeds, so we, therefore, must act in conformity to his good will, or as much of it as we understand. 4. In our view of God, Leibniz declares that we cannot admire the work solely because of the Maker, lest we mar the glory and love God in doing so. Instead, we must admire the Maker for the work he has done. 2. Effectively, Leibniz states that if we say the earth is good because of the will of God, and not good according to some standards of goodness, then how can we praise God for what he has done if contrary actions are also praiseworthy by this definition? 2. Leibniz then asserts that different principles and geometry cannot simply be from the will of God, but must follow from his understanding. Leibniz wrote, "Why is there something rather than nothing? The sufficient reason is found in a substance which is a necessary being bearing the reason for its existence within itself." Martin Heidegger called this question the fundamental question of metaphysics. Symbolic thought and rational resolution of disputes, edit. Leibniz believed that much of human reasoning could be reduced to calculations of a sort, and that such calculations could resolve many differences of opinion. The only way to rectify our reasonings is to make them as tangible as those of the mathematicians, so that we can find our error at a glance, and when there are disputes among persons, we can simply say, "Let us calculate," without further ado, to see who is right. Leibniz's calculus ratiocinata, which resembles symbolic logic, can be viewed as a way of making such calculations feasible. Leibniz wrote memoranda that can now be read as groping attempts to get symbolic logic, and thus his calculus, off the ground. These writings remained unpublished until the appearance of a selection edited by Karl Emanuel Gerhardt, 1859. Louis Couturat published a selection in 1901. By this time the main developments of modern logic had been created by Charles Sanders Peirce and by Gottfried. Leibniz thought symbols were important for human understanding. He attached so much importance to the development of good notations that he attributed all his discoveries in mathematics to this. His notation for calculus is an example of his skill in this regard. Leibniz's passion for symbols and notation, as well as his belief that these are essential to a well-running logic and mathematics, made him a precursor of semiotics. But Leibniz took his speculations much further. Defining a character as any written sign, he then defined a real character as one that represents an idea directly and not simply as the word embodying the idea. Some real characters, such as the notation of logic, serve only to facilitate reasoning. Many characters well known in his day, including Egyptian hieroglyphics, Chinese characters, and the symbols of astronomy and chemistry, he deemed not real. Instead, he proposed the creation of a characteristica universalis or universal characteristic, built on an alphabet of human thought in which each fundamental concept would be represented by a unique real character. It is obvious that if we could find characters or signs suited for expressing all our thoughts as clearly and as exactly as arithmetic expresses numbers or geometry expresses lines, we could do in all matters insofar as they are subject to reasoning all that we can do in arithmetic and geometry. For all investigations which depend on reasoning would be carried out by transposing these characters and by a species of calculus. Complex thoughts would be represented by combining characters for simpler thoughts. Leibniz saw that the uniqueness of prime factorization suggests a central role for prime numbers in the universal characteristic, a striking anticipation of Gödel numbering. Granted, there is no intuitive or mnemonic way to number any set of elementary concepts using the prime numbers. Because Leibniz was a mathematical novice when he first wrote about the characteristic, at first he did not conceive it as an algebra but rather as a universal language or script. Only in 1676 did he conceive of a kind of algebra of thought, modeled on and including conventional algebra and its notation. The resulting characteristic included a logical calculus, some combinatorics, algebra, his analysis situs, geometry of situation, a universal concept language, and more. What Leibniz actually intended by his Characteristica Universalis and Calculus Ratiocinata, and the extent to which modern formal logic does justice to calculus, may never be established. Leibniz's idea of reasoning through a universal language of symbols and calculations remarkably foreshadows great 20th century developments in formal systems, such as Turing completeness, where computation was used to define equivalent universal languages, see Turing degree. Formal logic, edit. Main article, algebraic logic. Leibniz has been noted as one of the most important logicians between the times of Aristotle and Gottfried. Leibniz enunciated the principal properties of what we now call conjunction, disjunction, negation, identity, set inclusion, and the empty set. The principles of Leibniz's logic and, arguably, of his whole philosophy, reduce to two. 1. All our ideas are compounded from a very small number of simple ideas, which form the alphabet of human thought. 2. Complex ideas proceed from these simple ideas by a uniform and symmetrical combination, analogous to arithmetical multiplication. The formal logic that emerged early in the 20th century also requires, at minimum, unary negation and quantified variables ranging over some universe of discourse. Leibniz published nothing on formal logic in his lifetime. Most of what he wrote on the subject consists of working drafts. In his History of Western Philosophy, Bertrand Russell went so far as to claim that Leibniz had developed logic in his unpublished writings to a level which was reached only 200 years later. Russell's principal work on Leibniz found that many of Leibniz's most startling philosophical ideas and claims, for example, that each of the fundamental monads mirrors the whole universe, follow logically from Leibniz's conscious choice to reject relations between things as unreal. He regarded such relations as real qualities of things. Leibniz admitted unary predicates only for him. Mary is the mother of John describes separate qualities of Mary and of John. This view contrasts with the relational logic of De Morgan, Peirce, Schroeder and Russell himself, now standard in predicate logic. Notably, Leibniz also declared space and time to be inherently relational. Leibniz's 1690 discovery of his algebra of concepts, deductively equivalent to the Boolean algebra, and the associated metaphysics, are of interest in present-day computational metaphysics. Mathematics, edit. Although the mathematical notion of function was implicit in trigonometric and logarithmic tables, which existed in his day, Leibniz was the first, in 1692 and 1694, to employ it explicitly, to denote any of several geometric concepts derived from a curve, such as abscissa, ordinate, tangent, chord, and the perpendicular. See History of the function concept. In the 18th century, function lost these geometrical associations. Leibniz was also one of the pioneers in actuarial science, calculating the purchase price of life annuities and the liquidation of a state's debt. Leibniz's research into formal logic, also relevant to mathematics, is discussed in the preceding section. The best overview of Leibniz's writings on calculus may be found in BOS, 1974. Leibniz, who invented one of the earliest mechanical calculators, said of calculation, "For it is unworthy of excellent men to lose hours like slaves in the labor of calculation which could safely be relegated to anyone else if machines were used." Linear systems, edit. Leibniz arranged the coefficients of a system of linear equations into an array, now called a matrix, in order to find a solution to the system if it existed. This method was later called Gaussian elimination. Leibniz laid down the foundations and theory of determinants, although the Japanese mathematician Seiki Takekazu also discovered determinants independently of Leibniz. His works show calculating the determinants using cofactors. Calculating the determinant using cofactors is named the Leibniz formula. Finding the determinant of a matrix using this method proves impractical with large n, requiring to calculate n products and the number of n permutations. He also solved systems of linear equations using determinants, which is now called Cramer's rule. This method for solving systems of linear equations based on determinants was found in 1684 by Leibniz. Cramer published his findings in 1750. Although Gaussian elimination requires O of open paren n cubed close paren arithmetic operations, linear algebra textbooks still teach cofactor expansion before LU factorization. Geometry, edit. The Leibniz formula for pi states that 1 minus 1/3 plus 1/5 minus 1/7 plus ... equals pi over 4 period. Leibniz wrote that circles can most simply be expressed by this series, that is, the aggregate of fractions alternately added and subtracted. However, this formula is only accurate with a large number of terms, using 10 million terms to obtain the correct value of pi /4 to 8 decimal places. Leibniz attempted to create a definition for a straight line while attempting to prove the parallel postulate. While most mathematicians defined a straight line as the shortest line between 2 points, Leibniz believed that this was merely a property of a straight line rather than the definition. Calculus, edit. Leibniz is credited, along with Isaac Newton, with the discovery of calculus, differential and integral calculus. According to Leibniz's notebooks, a critical breakthrough occurred on the 11th of November, 1675, when he employed integral calculus for the first time to find the area under the graph of a function y equals f, x. He introduced several notations used to this day, for instance the integral sign indefinite integral. The integral of f of x dx, representing an elongated s, from the Latin word summa, and the d used for differentials. Dy over dx, from the Latin word differentia. Leibniz did not publish anything about his calculus until 1684. Leibniz expressed the inverse relation of integration and differentiation, later called the fundamental theorem of calculus, by means of a figure in his 1693 paper Supplementum Geometriae Dimensoriae. However, James Gregory is credited for the theorem's discovery in geometric form. Isaac Barrow proved a more generalized geometric version, and Newton developed supporting theory. The concept became more transparent as developed through Leibniz's formalism and new notation. The product rule of differential calculus is still called Leibniz's law. In addition, the theorem that tells how and when to differentiate under the integral sign is called the Leibniz integral rule. Leibniz exploited infinitesimals in developing calculus, manipulating them in ways suggesting that they had paradoxical algebraic properties. George Berkeley, in a tract called The Analyst and also in De Motu, criticized these. A recent study argues that Leibnizian calculus was free of contradictions, and was better grounded than Berkeley's empiricist criticisms. From 1711 until his death, Leibniz was engaged in a dispute with John Keill, Newton and others, over whether Leibniz had invented calculus independently of Newton. The use of infinitesimals in mathematics was frowned upon by followers of Karl Weierstrass, but survived in science and engineering, and even in rigorous mathematics, via the fundamental computational device known as the differential. Beginning in 1960, Abraham Robinson worked out a rigorous foundation for Leibniz's infinitesimals, using model theory, in the context of a field of hyperreal numbers. The resulting non-standard analysis can be seen as a belated vindication of Leibniz's mathematical reasoning. Robinson's transfer principle is a mathematical implementation of Leibniz's heuristic law of continuity, while the standard part function implements the Leibnizian transcendental law of homogeneity. Topology, edit. Leibniz was the first to use the term analysis situs, later used in the 19th century to refer to what is now known as topology. There are two takes on this situation. On the one hand, Mates, citing a 1954 paper in German by Jacob Freudenthal, argues. Although for Leibniz the situs of a sequence of points is completely determined by the distance between them and is altered if those distances are altered, his admirer Euler, in the famous 1736 paper solving the Königsberg Bridge problem and its generalizations, used the term geometria situs in such a sense that the situs remains unchanged under topological deformations. He mistakenly credits Leibniz with originating this concept. It is sometimes not realized that Leibniz used the term in an entirely different sense and hence can hardly be considered the founder of that part of mathematics. But Hideki Hirano argues differently, quoting Mandelbrot. To sample Leibniz's scientific works is a sobering experience. Next to calculus, and to other thoughts that have been carried out to completion, the number and variety of premonitory thrusts is overwhelming. We saw examples in packing. My Leibniz mania is further reinforced by finding that for one moment its hero attached importance to geometric scaling. In Euclidis Preta, which is an attempt to tighten Euclid's axioms, he states, I have diverse definitions for the straight line. The straight line is a curve, any part of which is similar to the whole, and it alone has this property, not only among curves but among sets. This claim can be proved today. Thus the fractal geometry promoted by Mandelbrot drew on Leibniz's notions of self-similarity and the principle of continuity, natura non facit saltus. We also see that when Leibniz wrote, in a metaphysical vein, that the straight line is a curve, any part of which is similar to the whole, he was anticipating topology by more than 2 centuries. As for packing, Leibniz told his friend and correspondent Des Bosses to imagine a circle, then to inscribe within it 3 congruent circles with maximum radius. The latter smaller circles could be filled with 3 even smaller circles by the same procedure. This process can be continued infinitely, from which arises a good idea of self-similarity. Leibniz's improvement of Euclid's axiom contains the same concept. Science and Engineering, edit. Leibniz's writings are currently discussed, not only for their anticipations and possible discoveries not yet recognized, but as ways of advancing present knowledge. Much of his writing on physics is included in Gerhardt's mathematical writings. Physics, edit. See also, Dynamism, Metaphysics, and Conatus in Leibniz. Leibniz contributed a fair amount to the statics and dynamics emerging around him, often disagreeing with Descartes and Newton. He devised a new theory of motion, dynamics, based on kinetic energy and potential energy, which posited space as relative, whereas Newton was thoroughly convinced that space was absolute. An important example of Leibniz's mature physical thinking is his Specimen Dynamicum of 1695. Until the discovery of subatomic particles and the quantum mechanics governing them, many of Leibniz's speculative ideas about aspects of nature not reducible to statics and dynamics made little sense. For instance, he anticipated Albert Einstein's